Okay, class, this is an example. I've used the term cradle to grave, meaning complete, example of a t-test for 2 samples covering it all. All right, covering it all. First of all, you can download these on Blackboard, so you might want to have them, have access to them when we're going through them because there's a lot of math coming. And it would probably be best for you to have that in front of you when we talk about it. The first thing I want to mention here are the hypotheses right there. The research hypothesis, H sub 1, dogs will solve a treat puzzle faster than cats. Okay, so we're talking about 2 groups here, 2 samples, a sample of dogs and a sample of cats, and we're going to compare them regarding the amount of time it takes for them to solve some kind of a treat puzzle. Like, for example, if you put a treat inside a toy to see how long it took the animal to get the treat out of the puzzle. Now, we already know that we need a one-tailed test because this hypothesis has specified, this research hypothesis has specified direction, faster than. Now, don't be fooled, because even though it says faster, a lot of times people will put the critical region, the tail, on the right-hand side of the distribution. That's not correct. It needs to go on the left-hand side of the distribution because we're saying dogs are going to be faster, which means they're going to take less time. H sub 1, dogs will solve a treat puzzle faster, less time than cats. The null hypothesis, H sub 0, dogs will not solve a treat puzzle faster than cats. Okay, so these are our hypotheses, H sub 1 and H sub 0, and we need a one-tailed test because we're saying that dogs, our sample of dogs, will be faster than our sample of cats. You can see here, test at the 0.01 level. So now we already know quite a bit. We need a one-tailed test at the 0.01 level. A one-tailed test at the 0.01 level. Then here's some given information, and this is the type of information that you'll be given when you are asked to solve a t-test for 2 samples. We have our information for dogs, we have our information for cats. N sub 1 is 11, we got 11 dogs. The mean is 6 minutes, so it took our sample of 11 dogs an average, a mean of 6 minutes to solve their treat puzzle with a standard deviation of 2 minutes. Okay, dogs, 11 of them, average of 6 minutes, 2 minutes, or the standard deviation 2 minutes. Cats, 11 cats, average puzzle solving time of 7.5, standard deviation of puzzle solving time of 3 minutes. Now, we already have results in the anticipated direction, don't we? Which group, just don't pay any attention to this, to anything else that you may have already printed out, but which group, dogs or cats, were faster? The dogs are faster, right? The dogs took, on average, 6 minutes. The cats, on average, took 7.5 minutes. So the dogs are faster. But were they so fast to warrant rejecting the null hypothesis? Okay, that's the question that we're going to answer using our inferential statistical testing. Down below, on the same sheet, sheet number 1, down below, I have set up the probability distribution just like you would need to do in order to successfully solve this problem. I drew the bell-shaped curve. We've already established we need a one-tailed test on the left side of the distribution. That's right there. We know we were asked to solve this or to test this hypothesis at the 0.01 level. So the alpha region is 0.01, the body is 0.99. And I consulted the t-table using this information, 20 degrees of freedom, an alpha level of 0.01, one-tailed test. My t-value, according to the table, was 2.528. However, as you can see, I correctly indicated negative 2.528 because we are on the left-hand side of the distribution. Also, I put a little asterisk here reminding you of how to calculate the degrees of freedom. Degrees of freedom equals n sub 1 plus n sub 2 minus 2, or 11 plus 11 minus 2. 11 plus 11 is 22. 22 minus 2 is 20. Okay, page 1. Page 2. All right, page 2 is where we calculate data generated t. On the left-hand side, you can see I've repeated the t formula, all right? And you've seen this before. Data generated t equals mean for first sample minus mean for second sample divided by the standard error of the difference, the standard error for the two samples together. I'm going to stop talking about this left-hand column and start talking about the right-hand column, because here is really where the rubber meets the road in terms of solving this problem. It's really most difficult, as you've probably already surmised, to solve for the standard error, the denominator of the formula. All I did was repeat the formula you've already seen for when n1 is equal to n2. Our two sample sizes are the same. Standard deviation sample 1 divided by square root of n for sample 1, going to square that, plus standard deviation for sample 2 divided by square root of n for sample 2, going to square that. Add that together, take the square root. Here all I did was plug and chug. Standard deviation for dogs, 2. Standard deviation for cats, 3 minutes. Square root of 11, that's n1. Square root of 11, that's n2. And then I just simply solved one step at a time. I am not going to go through each step and explain each step because I'm assuming that this math is something that you're able to do correctly following the order of operations. However, here, as you can see, you have an example from beginning to end that you can look at. And as I mentioned a little bit ago, I did one step at a time in order to show you. So you should be able to retrace my steps backwards if you have any questions at all about where each item came from. And I just noticed I had an error that I just fixed. I added that square. I forgot to leave the exponent there when I was copying things down. So as you can see, just again, one step at a time, one step at a time, one step at a time, being very careful. And I ended up with 1.087. So that means that S sub x bar 1 minus sub x bar 2 equals 1.087. That number right there, 1.087, which came from all these steps resulted in that value, 1.087. That value is going to go into the denominator of my t formula. T equals mean for first sample minus mean for second sample divided by the standard error of the difference. T equals 6. That's our mean for our dogs, minus 7.5. That's our mean for cats, divided by 1.087, the standard error of the difference. That's where that came from, 1.087. 6 minus 7.5 is negative 1.5 divided by 1.087. T equals negative 1.380. This value, 1.380, that is the amount of standard error between our means. 1.380 units, and that language is very important. 1.380 units of standard error separate our means. All right? Now it's negative simply because of the order in which we place them based on the hypotheses. How would this look like on the drawing? Page 3. Well, hopefully this drawing is familiar. It's the same one you saw before. Bell-shaped curve, rejection region on the left side, rejection size of 0.01, that's our alpha level. That means this has to be 0.99. Our t value is negative 2.528. That came from the table. Our legend is right here. Degrees of freedom is 20. Alpha level is 0.01. This is a one-tailed test. Where did our data-generated t value fall? It fell right there. It did not exceed. It did not exceed. It did not go further into the tail. It's in the body. Therefore, the data, this is very important, don't blow this off. The data-generated t-value did not fall in the rejection region. The amount of standard error we observed can reasonably be attributed to sampling error. But I added something as well. This is a very important point. Let's bring it back, always bring it back to the hypothesis. Dogs don't appear to be faster than cats at treat puzzles. Dogs don't appear to be faster. They had less time, but they weren't so much faster that it warranted rejecting the null. They are statistically the same, dogs and cats.